Let us now derive some of the closure properties of regular language, and particularly regular languages have lots of closure properties. So we have already proved closure for union, concatenation, and clean star. So if you go back to that regular expression video, so there the strategy was first given, say, DFA for a regular language. We modified it such that it has only one final state. So it has one start state and it also has only one final state, and the modification was you take all the final states in the given DFA and then put this epsilon transitions to this unique newly created final states, and these states are no longer final state. So once we have this thing, so which we show as black box with one start state, one final state. So this was a construction for union of two regular languages. So this accepts, say, something L1, this accepts, say, something L2, and then this accepts union of L1, L2, and this was even easier. So it accepts this concatenation of language accepted by this and this. And then clean star was slightly more non-trivial. But nonetheless, it's not very hard to see that this accepts this clean star of this LM, where LM is just this part. So we have already discussed this thing while discussing regular expression. So you know that that regular languages are closed under union, concatenation, and clean closure. So the next thing we will address is closure under complement. So what was complement? If you remember from the very first class, we defined this thing. So you have some language over some alphabet sigma, right? So the complement is just the set theoretic complement where this is your universe. So this minus this set. Okay, so this is that's what the complement is. Now this theorem says that if L is regular, so we can define this complement for any language, whether it's regular or not. So this theorem says that if L is regular, so then its complement is also regular. So if L is regular, then this is regular. And the proof is very simple. The idea is you take a DFA for this language L. Since this is regular, there must be some DFA which accepts this L, so you take that DFA. And it is important that you take a DFA, not a NFA, not a epsilon NFA. You should take a DFA and with total transition function. This is also important. Now, if you have something which is not total, you can introduce this dead state to make this total, so that we discussed while discussing dead state, right? If you forgot, then just go back to those things. So, but without loss of generality, we assume that this whatever finite automata we are discussing, that's a DFA and that has total transition function, and that accepts this given language, given regular language L, right? So that has some final set of final states. There can be multiple final states. Okay. Now the new DFA that we construct to accept this language is this one. So see, everything is same. This Q is same, sigma is same, even transition function and the start state is same. The only difference is in this final state. So it's just the complement of this F. So a state, so something is final state here if and only if it is not final state here, and vice versa. This is a final state here if it is not a final state here. Okay, so that's what this complement says. So then what do we need to prove? That this is the language is indeed complement of this thing. So by definition, so this is what we need to prove, that this so for any string, this string belongs to this L, which is L of m, if and only if, so this is if and only if this does not belong to sorry, this is m, this is m prime. Just to make this correction, this is m prime. Okay, so if and only if this does not belong to this L of m prime, right? So this is what we need to prove in order to show that the language of m prime is actually this complement of L, and it's just this one line proof. So when is this accepted? This is a DFA, so this is the acceptance condition, that's starting from Q0 if you can reach some state in F, because F is the final state in M. So acceptance in M, that means the state you reach is F, and you say this, so that means so this means that it holds if and only if this is not in the final states here, right? And this means that so this holds if and only if it is not accepted by this L of m prime, right? So now this step, you see that you reach some final state, so that means and this is not in this thing. So this requires this delta to be total, because you see in fact not this part, in fact this part actually requires this thing to be total. Why? Because if it is not total, then rejection can mean that it got stuck. Okay, acceptance means it reached something in final state, so that will be one way sort of implication. So this from here to here the implication will be there, but say if it is not accepted, so that can mean that either it reached something which is not in F or it got stuck. So this getting stuck we don't want to deal with, so that will make this proof complicated. So to begin with, we choose this with total transition function, right? So and yeah, so that's the proof. And just to emphasize my point that this does not work with this partial thing, so I have an example. So take this finite automata. So this is a DFA, but the transition function is not total. Why? Because so the alphabet is just this A. So from every state we should have a transition on A if this is total, but so from here we do not have any transition, right? So from this state there is no transition on A, so this does not accept A, because it takes A and then it gets stuck. But that happens because we are using this partial transition function. But anyway, so the language accepted by this thing is just this singleton set containing A, right? That is immediately clear. So now if we switch the final state, so what is happening here? We are just switching the final states. Whatever is final here is non-final here, whatever is non-final here is final here. So just this switch. So if we do that, that means this non-final state becomes final, this final state becomes non-final. So if we do this, then what is this thing? So this accepts epsilon, right? Because the start state is final state. So then it can accept A, but it will reach some non-final state. So then if you give it another input, it will get stuck. So both for this A or A followed by some other number of A's, so that will be rejected, right? So the only thing that is accepted is this epsilon. But you see that this is not complement of this, right? So complement of this is what? So if this is your sigma, then sorry. What is this? So this is again a typo. So this what I meant here is that what I meant here is for L equal to this language, for L equal to this, L complement is equal to this language, right? L complement is this, but you see that here we do not get the complement, right? So please make this corrections. So now, as I said, it will work if we had a total transition function. So if we introduce, say, some dead state. So what was the strategy for introducing dead state? So whatever transition is not present in your DFA, you make a transition to the dead state. So here this is our dead state. So this transition, there is no transition from here, so we make this transition to the dead state. And once you are in dead state, you remain in dead state no matter what input you get. So this is the correct way to introduce dead state for this machine. And now the transition function becomes total, right? And now if we do this trick of clipping this final states, so then this is what we get. So these two non-final states are then final, and this final state becomes non-final, right? And then what is the language here? See, epsilon is accepted because of this. Then if you put A is not accepted, right? Because you are in non-final state. But then if you put another A, you come here, and then for any subsequent A, you remain here. So this A square, A cube, A4, so all these higher powers of A's are accepted. And you see that this is indeed, so again, this is L, and this is what so this is L, and this is this L complement, right? So now also this will not work with NFA. So again, this some example. So yeah. So what is this NFA? You see, it can take some number of A's and then it will take another A and it will reach the final state. So it will take A square, A cube. So it's just this A's plus. Plus means non-empty string, right, over this alphabet. But now if you flip the final state, so this is what you get, and what is the language here? So you can take as many A's here, and this will give you A star. Okay. So again, this thing does not work with NFA or partial transition function. But if you have some NFA or whatever, epsilon NFA, partial transition function, whatever, you can also have a DFA with total transition function, which accepts this language. So you start with that DFA, and then you construct this DFA. So this will also be a DFA, right? And we show that this DFA accepts this L prime. So if some language is accepted by some DFA or finite automata, then that language is regular. So this is regular, right? The next thing we address is the intersection of regular languages. So we did union, concatenation, clean star. Intersection should have followed immediately, but you see that intersection is so you will see that for example in CFL intersection doesn't hold, though union and clean star and concatenation holds. So but anyway, the proof is very simple. So again it uses the previous result that regular languages are closed under complement, and complement has this property that if you take complement twice, so if you take complement once and then complement twice, so then you get back L, right? So from L you get the complement of L, and again the complement of that is L itself. So you take two regular languages, L1 and L2, they are say both regular, and the theorem says that their intersection is regular. Why? Because you start with this intersection, you take this complement twice, and then there is this set theory equality, and you all know this thing, right? So if I have this intersection, this then this, so this is what, this union this, so it okay. So it's well known identity for, it holds for any set, not just language or anything. So yeah, this is what we did here. But now see what's happening. So we will use the previous closure properties. So we know that this L1 complement and L2 complement are regular by the previous theorem. And then we know that if I take union of two regular languages, that is also regular. So I take the union of this regular language and this regular language. So this is regular, right? And now if this is regular, then I again take complement of this thing. So this is regular. Okay. And this is exactly this thing, this thing. So the proof is just this one line proof. But you see, with each proof we are also giving a way to construct the corresponding automata. So all the proofs are kind of constructive. So in case of union, concatenation and clean closure, we gave this construction, right? And in case of complement also, we gave this construction. So now here you can construct, so given say some automata for L1 and L2, so first you convert that to some DFA, and then you flip the final states, and then you take their union. But when you are taking union, you will introduce epsilon transitions, right? But in order to do this complement, then you have to convert whatever epsilon automata you epsilon NFA you have for this part. So for this part you will have some epsilon NFA, but to make this complement you have to convert that epsilon NFA to DFA, and that might blow up the number of states exponentially, and so all this multi-step process gives you a very complicated looking automata for this intersection. So there is another way to sort of, it's a more direct way to attack this problem. So that is through product automata. Okay. So again we are proving the same theorem, but it's an alternative proof, and the idea is called product automata. So in fact you have already seen this in a problem we did before. So now suppose you have two DFA. Okay. So you can do the same thing with NFAs also, but just to keep things simple, let's just consider DFAs. So now they have they have same input alphabet. See, this sigma and this sigma is same. Everything else is different. So they have different states. They have different start states, different transition functions, and different final states. But both are DFA. Okay, with same input alphabet. Now the product of these two automata is another automata which is defined like this. Okay. So the state is a product of the set of states here and set of state here, right? So if say Q and P are states here and here, so a state here will look like, say, a pair QP, right? And then we have to define this transition function. So this transition function is just this. It captures these two transitions in just one equation, right? So suppose in your M1, so this is for M1, this delta Q is for M1 and delta P is for M2. So suppose in this M1, from Q on A you move to Q prime, and in this M2 from P on A you move to P prime. So you make a transition in the product automata like this, because this is a state in your M, because states are now pairs of states here and here, and on A you move to this pair, right? So we can, this is a valid transition function. So you see that this equation is just kind of combining these two separate equations. Okay. And then what are what are the final states? Again, the final state is all the pairs where both the components are final states in M1 and M2 respectively, right? So if you have some final state here, so it will look like this FQ AP, where this FQ is some final state here and this AP is some final state here, right? So what is it doing? See, a transition here. Okay, so if you consider a say accepting path, this chain of transition in this product automata, so it will be something like that. So on each input symbol it moves from state to state to state, and finally it reaches some final state, and final states look like this. So both components are final states in M1 and M2 respectively, right? But this is a final state in here. So now if you have this thing, when can you have this thing? So you can have this thing if and only if you have these two paths in M1 and M2 separately, right? So this is a if and only if condition, because this transition is just putting these two transitions together. So we have these two paths if and only if we have this single path in our product automata, and vice versa. So it's a if and only if condition, right? So yeah, this Q0 P0 goes to Q1 P1 goes to Q2 P2, right? But what does this say? This says that this string, if you consider, if you are considering this W, which is A1 up to AN, so this is part of this L1 also, and this is part of this L2 also, right? So that means it is in the intersection of L1 and L2, and it is in the intersection of L1 and L2 means that it is accepted here, and it's if and only if condition. It is accepted here if and only if so it is in the intersection of this L1 and L2, right? So this automata gives you a direct construction to to accept this L1 intersection L2. Okay, and if you want a formal proof, you have to use induction on the length of the input string, right? And then what is the acceptance condition in this product automata? So this is the start state, and if you begin with the start state and process this W, you should reach some final state in product automata. In product automata, the state of final state is this. This should be FQ, this should be FQ, and this should be FP. Okay, so because we have taken FQ and FP here, so you have to prove that this happens if and only if both of this happen separately, this and this. So on one hand you have this thing, so this and this, and other hand you have this. So you have to show that there is a if and only if between these two, and this means that we are talking about this L1 intersection L2, right? And this means that this language is same as L of M, whatever we are considering. So that's the proof. Just to give you an example, so consider this two automata. So call this M1 and call this M2. So what is the language here? You see, it can take any number of ones. Then if it sees 1 0, then it moves to this non-final state. Then it can take any number of 1, and then with another 0 it comes back here. So it's in this state if and only if it has seen even number of zeros. You see, it can take any intermediate ones, any number of ones at any point, no matter which state it is in. But in order to be in this final state, it must see even number of zeros. So some number of ones, 0, then some number of ones, then another 0 comes back, then some number of 1, then a 0, then some number of ones, then another 0, it comes back. So if you have even number of zeros, only then you come back to this thing, this state. So this accepts all strings over 0 and 1 with even number of zeros, right? And it's the same construction, only the zeros and ones are switched. So it accepts all strings over 0 1 with even number of ones. It's the same thing. Okay, but now if I take the product, so the start state is the pair of start states here. So this is Q0 P0, and then say on 0 what happens? On 0, this Q0 moves to Q1, P0 remains in P0. So Q0 moves to Q1, P0 remains in P0. So these pairs are now states in this new automata, right? So in this way, you capture the parallel transition in these two machines as a single transition between this pair of states here. So if you do this, you get the intersection, which is even number of zeros and even number of ones. So we get this intersection here. So in fact, this is one of the very first automata we discussed when we started DFA. So you can think of constructing this thing out of these two smaller, simpler thing, and then somehow composing these two to get this one. So next we define quotient of languages and define improve closure property for regular language. So quotient of two languages, say L1 and L2, and L1 L2 need not be regular, so we can define the quotient for any two languages. So take any two languages, L1 L2. So the quotient of L1 and L2, it's written like this, L1 slash L2. So the quotient is the set of strings such that this string is a prefix of some string in L1. So xy is in L1 and x is a prefix of this string. So this prefix is in this quotient, but with the constraint that the remaining part, so this is the prefix and this is the suffix part. So with the constraint that this suffix part is in L2. Okay. So any x will be in L1 quotient L2 if there exists some y in L2 such that this xy it's in L1. So that's the definition. So now just take some moment and try to understand this thing and make sure that you do not misunderstand the definition. For example, if we talk about this thing, so here I have expressed the language in terms of regular languages. So what are the strings here? So in here you can have some, say I many zeros, and then some 1, and then say this j many zeros again. And from here, so if this is in your L1, okay, so that means you should be able to break it down into two parts so that you can take out this suffix part on the constraint that this suffix part belongs to L2. So that means you have to somehow break it down so that you can take out something. So what can you take out? You can either take out some 0, 1 and then remaining 0, or you can take out some zeros. But here this y should be part of this thing, and this thing contains two ones, you see. So this contains two ones, right? But this contains just 1 1, right? So you cannot take out this y from any string here. So that means there doesn't exist any such x for which these constraints are met. So that means this set will be empty. No such x are there. So that is why this quotient is empty, right? Similarly here you are now taking out strings of the form this 0 to the j1. So in general, again, this can be, say, some 0 to the I, then 1, and then say 0 to the k. And from here you are taking out some suffix part, provided that suffix part is in this language. But this language means whatever y we are talking about, this y, that y has to be of this form, right? But then this thing, I mean, we cannot just take any string from here. So the only x for which we can have this xy in this language will be such that this xy ends with this 1, right? So xy must end with this 1. So that means okay, so this sort of strings are here. So that means we can only think about the xy which has this form, and then if we take out this y from here, so x is the remaining zeros, right? And now here you can have any number of zeros because this I minus j can be any integer. So that means whatever x you have here, you can have any number of zeros. So this is precisely a 0 star. Okay. So just be careful when trying to compute this quotient. For example, I have seen students making some silly mistakes, like they take this and then they take the quotient this, and then they claim that this is 1, so which is not true, right? So this is not 1. So what is the right answer? The answer is again 1 0 star. And why is it so? You just figure it out. You just go through this definition and see that you understand that this is indeed 1 0 star. Okay, so this is the definition of quotient. Now the theorem says that if L1 is regular, then L1 quotient L2 is regular. So what about L2? L2 can be any language. Okay, L2 need not be regular. So this is the beauty of this result, that in the previous result where we had two languages, say L1 union L2 or L1 intersection L2 or L1 concatenation L2. So in those cases we required both languages to be regular. But here, if only L1 is regular, then no matter what L2 is, this L1 quotient L2 will be regular. And the proof is again very simple. It's almost like a one line proof. So since this L1 is regular, we take a DFA for this L1. Okay, and then we construct another DFA M prime and claim that the language of this M prime is so the claim is that the language of this M prime, this is L1 quotient L2. This is the claim. Now how do we define this M prime? See, this Q, sigma, even the transition function, start, state, everything is same. The only difference is in this final states. Okay, and how do we define these final states? So these are all the states such that from this state we can reach some final state. Okay, you start from this Q and you process some Y to reach this final state, such that this Y is in L2. Okay, so any such Y will do. So so in this new setup, you have some state Q. Okay, so then you just see whether there is any Y such that you can reach something in F. So if that is the case, then you make this to be your final state in the modified DFA for this M prime, right? That's it. And then the proof is immediate, because then what do we need to show? That okay, so you see this state, okay, is in A prime. There is some state. You start with this Q0 and process some X. So our goal is to show that this X is a prefix of this XY, where Y belongs to L1. So okay, we take this X and we move process this X and we move to something, and then this X will be accepted if it falls in this F prime, right? By the way, by the way we have constructed this thing, since this is deterministic, this is a DFA, right? So there's a unique path we are talking about. So it reaches a unique state, and that state is in F prime. That means by this definition, okay, from this state that it reached, from this say call this Q, so this thing, so this thing you call say Q. Okay, so by this definition, from Q there is a path to F for this original DFA on some y such that this y belongs to L2, right? So there exists y in L2 such that from here, from this Q, if you process y, this further thing, so then you go to this F. So that means what? So what is this thing? So starting from Q0 you are processing X, then you are processing Y. So this thing is nothing but this thing, right? You are processing XY, right? And this is saying that this XY is in L of so this XY is in L1. So if you put this together, so this thing is equal to this thing. So this and this together tells you that this delta hat Q0 XY, so this belongs to F, right? So that means this XY is a string in L1, okay? And this part, so this condition says that X is in this L of M prime, right? So this thing says that X is in L of M prime, and this X is in L of M prime if and only if we saw that there exists Y in L2 such that this XY is in L1, and this is precisely the definition of L1 L2, and there is a if and only if. Okay, is a if and only if. So this thing is accepting L1 quotient L2. Okay, so that's the proof. So if you want to visualize it in your mind, so what we are doing is here we have Q0, okay, and as I said, in any state we make it we put it inside this F prime if there is some y, so some y in L2, okay, such that after processing this thing you go to somewhere in F, right? There can be multiple, okay, and then you are seeing what if I say process X and it lands in some state in say F prime. So that means if this is the case, then this X, Y together, X here, Y here together, so that takes you from Q0 to F. So that means this XY is in L1 and this Y is in L2. So this is in L1, L2, and this is if and only if condition, the way we have done this thing. So that's the thing. Okay, so this is if you see Hofcroft-Woolman, this is given as an exercise, okay, not as a proved theorem. But if you see Hofcroft-Motwani-Woolman, so as I said, that book is kind of more verbose, and anyway, so it puts this thing as a theorem in the main text. But even if you think it as an exercise, this is an important exercise. So sometimes this property is used for other problems. So it's better to just emphasize this thing. So what we mean by reversal, so you take some string, okay, so these are symbols a1 a2 up to an, these are symbols, so these are part of sigma, and this is a string, okay. So the reversal is if you just reverse this symbol, so instead of a1 up to an, you take a1 up to a1, so an minus 1, an minus 2 up to this a3 a2 a1. So just read it from the opposite side, so that's the reversal of this thing. So this is not a power, so this is not r w multiplied r times, no, I mean, this is just a notation to say it's reversal, it's not power, okay. Now if you take any language over the sigma, say L, so the reverse of that language is defined like this. So you take the strings in L, and this LR contains a reverse of all the strings here, okay. So if you reverse all the strings in L, you get LR. So, and it's quite easy to see that if you take reversal twice, then you get back the original string, right? If you take this and then again if you take this, so you get back this thing. So the same is true for the language also. If you take this and again take this, so then you get back this language, right? So the theorem is that if L is regular, then this reverse of L is also regular, okay. So again, just pause the video and try to understand the definition. And fine. So the way we prove it is again we consider some, say you first consider some DFA. It can have multiple final state, okay. So suppose these are final states and this is a DFA that accepts, but then in the union, clean closure and concatenation, and when we did this regular expression, and also in the beginning of this video we said that we can convert this to epsilon NFA with a single final state, okay. So this has just one final state, so these part are same, so these final states are no longer final. We make this epsilon transition and put this one single final state, a new state, okay. So this we have done before. So without loss of generality, our finite automata has a unique final state, and that thing accepts L, right? So now in order to construct a automata for this LR, all we need to do is to just reverse the sign of this arrows, okay. So you see this picture, all the arrows are reversed, so instead of going from here to here, here to here, the arrows are reversed, okay. So and that's it. So the labels will remain same. I mean, if you have some label A here, so you also have that label A here, and the states are also same, so everything is same, just the direction of the arrow is changed. So how do we mathematically express that thing? See, these are NFA, so this delta and delta hat, so they are set of states, right? So what does the arrow mean? So from say P to Q, say we have this sort of arrow in M. So this means that if you take P and if you process A and take this transition, then Q is one of the states that you can move. So Q is one of the states, right? So Q is in this thing. So that's the thing for NFA. If it is a DFA, we could have put equal to here, but here we have to put Q is in this thing. So we reverse the arrow, means now the arrow goes from Q to P, right? So it goes from Q to P. So if this is the case in this sorry um, sorry, I reversed the thing. I should have put it's okay, I should have put R here and R, maybe M here. Yeah, so it's same. So yeah, here the arrow is from P to Q, and here the arrow is from Q to P. So, and say this is in MR, this is in M. So we put this arrow in MR if and only if we have an arrow of this sort in M. So that means if we have this P in delta QA, so then and only then we put this Q into delta R PA. So this transition function completely defines this transition function, and this is the thing, the same thing as reversing the arrows, right? And now you can clearly see why this should accept this reverse of a string. So if you are accepting if you have an accepting path here, okay. So now here you may have epsilon transitions, because we have introduced epsilon transitions, though I said that this part you can take as a DFA and then only this part is a epsilon, so only this AN will be epsilon. But anyway, the point is if you have such a path from start state to this final state, this one final state that we have, and by the way, here this final state becomes a start state, and this start state becomes the final state, okay. So yeah, so here if you have accepting path, this is accepting path because it goes to a final state from this start state, right? So then what is the string that you are accepting? You are accepting the string so here you are accepting the string A1 A2 up to AN, right? So this is the thing that you are accepting, right? And now if you have a path here like this, since the arrows are reversed here, you have a path from QF to Q0 here. But then what is the string that you are accepting in this accepting path? This is the final state here, right? So, and this is the start state here. So here also you are starting with the start state and reaching a final state. So you are accepting this thing in MR, right? But what is the string that you are accepting? It's AN, AN minus 1 and so on, right? So you are accepting a string AN, AN minus 1 and so on up to A2 and then A1. And this is nothing but this WR, right? So you are accepting this W, and this is if and only if, right? You have a path like this if and only if you have a path like this. So you are accepting W by M. So if and only if you accept WR in MR. So you see that MR is precisely this thing, and I have not written the full proof, so but it's just induction on the length of accepting path, okay. So it is it's almost same as say the length of W, but since we also have epsilon transition, so some of these things can be epsilon. So the length of accepting path can be in fact more than this length of W. So instead of taking this length of W, if you do the induction on length of accepting path, then it's much cleaner. So the argument is much more cleaner. So Yeah, you just use induction to show it both ways. Like if W is in LM, that means WR is in L of MR, and if WR is in L of M of R, then it implies that W is in LM. So both ways you show. So it's a if and only if, and that's it.